to deal with them numerically. And then towards the end, I will talk about some computational results. Okay, so when you approach computation of optimal control for fluid flow problems, and pardon? Oh yeah. So situation is different depending on whether you have linear PDEs or non-linear PDEs, and also so let me talk about optimal control of fluid dynamics. This also falls under another well-known class of problems known as PDE constrained optimization problems. So in that context, optimal control of fluid flow problems involves PDEs, that are Navier-Stokes equations, and therefore they are infinite dimensional nonlinear control problems because Navier-Stokes equation is nonlinear, and they are large scale because roughly speaking the number of degrees of freedom n is proportional to Reynolds number to the power 904. So as Reynolds number increases, the number of degree of freedom or number of say unknowns you have to resolve or compute increases. Linearization to deal with nonlinearity in Navier-Stokes equation is in general not acceptable, because what you compute ultimately is linear control, and of course you can go back and put it in the nonlinear problem and try to control it. It may not work because the linear control may have limitation in terms of convergence and other things. So you could look at feedback control, optimal feedback control problems. Again, because of the nonlinearity in Navier-Stokes equations, if you want feedback control, only way to obtain is using this dynamic programming approach, and that would lead to Hamilton-Jacobi-Bellman equations, which is computationally costly, at least at the moment, although you could employ reduced order modeling approaches if that is acceptable for your situation. So there is also general approach and numerical methods available for finite dimensional constraint optimization, and therefore people tend to approach this infinite dimensional control problem by first approximating, converting the whole problem into a finite dimensional framework and try to use it. But with infinite dimensional problems, there are unique issues that are important. For example, the choice of state and control spaces and the precise characterization of Lagrange multipliers or adjoints, optimality conditions with control and state constraints, mesh independence, convergence behavior. So these things warrants looking at this problem from an infinite dimensional point of view. So suppose we have a abstract optimal control problem. Let's look at this to see what sort of issues we come across. Suppose we have a post functional and that we want to minimize subject to a constraint, and in this case, in our case, it is Navier-Stokes equations. And U is the state and G is the control here. Okay. So when we approach numerically to try and compute the control, we often distinguish two approaches. One is first discretize and then optimize. That is what I mentioned a little earlier. That is, you first discretize the entire problem, convert it to a finite dimensional problem, and then optimize. That means you try and apply the optimization or control theoretic techniques for the discretized problem. Okay. The other approach is to first optimize or control, get the, say, maximum principle or feedback law, and then finally bring in the discretization, numerical techniques and so on to get the answer. And these two operations are not necessarily commutative, but under certain circumstances, these two approaches lead to the same result. So let's look at these two a little more in detail. So in first discretize, then optimize approach, what you do is you first discretize all the function spaces involved, cos functional, integrals in the cos functional, and the duality, etc., and get a discrete representation, and formulate a discrete minimization problem. So you have discretized cos functional that you minimize subject to discretized state equation. Okay. So here is an example that shows this discretize then optimize approach doesn't always work. This is due to Bill Hager. This example is actually for an ODE problem. Here we are minimizing, he just constructed this problem to demonstrate the difficulties in this approach. So you're minimizing a quadratic cos functional, okay, subject to this linear ODE. So you have initial condition here, okay. And this problem is, quadratic cos and linear constraint. It's such a simple problem, so you can actually exactly solve the state and control. Okay. What you do is you write down the optimality condition. Since you have quadratic cos and linear constraint, the necessary conditions are also sufficient. So simply you have to solve the state and adjoint equation and the maximum principle, and you get the solution. There's a bunch of coupled ODEs. So you can get this explicit expression, analytical solution. On the other hand, if you discretize this cos functional, you have to apply some numerical technique. Okay, it's a simple integral, one-dimensional integral. You apply midpoint rule. Okay, you get this discrete representation of this control. Okay, that is nothing but midpoint rule. For the state equation, he uses a second order Runge-Kutta method. Okay, that's what you get, second order Runge-Kutta. If you solve this problem, okay, again, deriving the optimality condition and the maximum principle, you get this as a solution for each k. So you are discretizing this time interval 0, 1 into k subintervals, and so you have k going from 0 to k. Solve this discrete problem, you get the solution. And what is it? What kind of solution is this? See, obviously it's not converging, right? See, it's oscillating between 0 and 1. So this illustrates this discretize then optimize can fail in some situations. This is of course a discretization issue. So here is another issue with this discretize then optimize approach, the convergence and discretization of the adjoint equation. If you look at, okay, this is the continuous problem, the state equation. If you derive the adjoint equation, you get this, okay, with the final condition. This is the maximum principle, okay. And whereas this thing, okay, this is a discrete problem. If you derive that, derive the optimality condition, that is the adjoint and the maximum principle. This is, the scheme is kind of derived from the scheme that you used here, the numerical discretization. See, here you don't discretize this, the discretization for the adjoint equation is dictated by the discretization that you used for the state equation. Whereas here, you could discretize these two separately. You can apply one scheme here and whatever other scheme is suitable for this problem, okay. And say if you apply Runge-Kutta for this, you won't get that, okay. If you apply to Runge-Kutta, you get that, but applying Runge-Kutta to this, you don't get this, okay. Okay, so the convergence behavior can be different, okay. And also in discretized then optimized approach, if you when you in the PDE context, that example is for ODEs, the spatial discretization is dictated by the test space that you use to discretize the state variable UH. Okay. Whereas in optimized then discretized, this can be different. You have the freedom of choosing the approximation for the state and adjoint independently. Okay. So in first optimized then discretized approach, how you start off is you first derive the first order necessary optimality condition, then discretize state and control. Then you have the freedom of choosing the discretization for the state and control, depending on what you think is suitable. Okay. So if you choose the spatial discretization pace for state and adjoint variable in the optimized then discretized approach, then it leads to optimality condition that are identical to the discretized then optimized approach. Choosing a different spatial discretized version can lead to difficulties if you choose to do that in subsequent optimization algorithm development. For nonlinear problem, people have found out optimized then discretized approach may lead to inexact gradient in the cost functional in some cases. This is a purely a numerical thing, but in theoretically you can prove these two gradients of the cost functional converges in some suitable norm as the parameter, the discretizing parameter approaches 0. So is there a general guideline for selecting the right approach? Well, there is none. It depends on the problem you are working with, and the only way to select the right approach is to investigate the discretization scheme for the optimal control problem you have, and you have to take into account of the structure of the problem, and also it depends on the computational resources available to you. So from now on, I'm going to focus on optimize then discretized approach. Okay, that is more closer to a numerical analyst. So here also we distinguish two approaches, two different broad classes of methods. One is non-intrusive methods, also known as black box method. The other one is intrusive method. I will explain to you what I mean by intrusive method later, also known as all at once method. So in non-intrusive approach, you treat the state variable as a function of control. You have seen this earlier when Nandakumaran gave the talk. He gave a ODE example where he eliminated the state by substituting that in the cost functional. That is what I mean by non-intrusive approach. You somehow, it's not always possible to eliminate the state because you cannot get the solution explicitly. So it's a kind of abstract map, okay? There in the intrusive approach, you treat the state and control as independent variables, okay? Okay, so let's look at this non-intrusive method. Here we, as I said, reduce the problem. If you have a constraint minimization problem, right? If you have you want to minimize the cost function subject to a constraint, and you have to assume this state to control map produces a unique output. In other words, given control, you have a unique output. If that is the case, that is basically, you assume the state equation has a unique solution for a given control input. If that is the case, you can take that and eliminate in the cost functional. So you substitute that the constraint into the cost function, okay, and eliminate the state in a sort of abstract map. Then you have reduced problems. You just have to, so basically this is an unconstrained minimization problem, okay. So you minimize this j hat, that is a reduced cost functional, where you eliminated the state by substituting the solution u, right? Okay, so This problem has a few advantages. For example, you can use existing PDE solvers and embed it into the optimization loop. And of course, you had to supplement this with gradient information of the state and so on. But this is quite convenient to work with. But on the other hand, it has difficulties. It can run into difficulties if there is lack of uniqueness in the constraint, if you cannot find a unique solution. Okay, for example, this problem, look at this optimal control problem. We are minimizing a quadratic course involving L2 norm of the gradient and involving a course function for the control, and subject to the Navier-Stokes equation. The control is acting on the right hand side, G is the control. This steady state Navier-Stokes equation. Okay, and it is well known that this Navier-Stokes equation doesn't have a unique solution unless you assume the viscosity is small enough, or viscosity is large enough and the control is small enough. Okay, so unless you assume viscosity is large and control is small, this problem doesn't have a unique solution. Okay, so you don't have the map that you can use. Okay, so let's assume viscosity is large enough and the control is small, so that we have a unique solution to this problem. I'm going to use this as a model problem to explain some of the techniques. Okay, so this course function represents here tracking a desired velocity. Okay, by applying control. Okay, control I'm taking it just for the sake of explaining things for simplicity. I'm taking the control is on the right hand side. Okay, so we apply this control G to drive the velocity to a given desired velocity. Okay, let U of G be the control to solution map, and let's assume that is unique. Yes.
Why do you really assume that mu is large or G is small? But as far as I remember, when we discussed this here, you can have solutions even for mu small.
Well, this is a steady state. Huh?
So
Steady state problem in 2D and 3D don't have a unique solution unless you make some assumption about.
yeah, but
there are a unique solution. Yeah.
no, you have solutions.
Yeah, it's not unique.
Yeah, and what's the problem with uniqueness here? You can all still define the energy.
Yeah, right. But
You
to
minimize all the solutions to your problem.
yeah, you probably missed what I said earlier.
Probably, yes.
See, define. Sorry. See, I want to reduce this constraint minimization problem. Okay, this is the problem I'm looking at. Okay, I have a course to minimize subject to this constraint. Okay, this problem, constraint minimization problem, can be converted into an unconstrained minimization problem. Here you eliminate the state by solving this uniquely and then put it in here in the course function. Then you just have a course function to minimize.
So then you want uniqueness.
Yeah, that is one way. Yeah, that is one way to approach this. There are other ways. Okay, I'm just trying to illustrate that thing. That if unique solution exists, then you have a convenient numerical technique. Okay, the reduced problem is easy to work with computationally. Computing gradient and all those things. Okay. Okay, so formally eliminating this state equation and putting the solution U of G, I can get rid of this constraint. I have reduced cost functional. Okay, so this one take care of the constraint. So I just have to minimize this unconstrained. Just have to minimize this cost function. Okay, constraint is gone. That is implicitly sitting there. Okay. That will help me update the control and things like that when I actually compute. Okay. Okay. So let me first talk about the steepest descent method. Since the control problem we have with Navier-Stokes equations are all non-linear problems, so all the methods are inherently iterative in nature. Okay, And the gradient based methods are the best methods because they converge faster. You want gradient free methods, that will just impossible to use those methods. Okay, with nonlinear problems, those are just too slow. So this is the basic method. Still, it has nice properties. I will show you a little later. Let's look at how this works. First, you need to get the gradient of the cos function. Okay. So it once you have a gradient, it uses negative gradient as stage direction in each iteration and updates the control. Okay. So we need the gradient computed. So gradient of the cos function. So I'm now looking at this reduced control problem. Okay, so this is my cos function, j hat. Okay, so derivative, that what I mean by derivative here is the Gatto derivative. I want to compute the Gatto derivative of j hat at the control g, which is j prime. Okay, and that belongs to a dual space. So we have to apply this Riesz representation theorem to come up with a gradient expression. Okay, so this gives you the derivative acting on this delta g, and this duality pairing is equal to the inner product between the gradient of j. This quantity is what we call the gradient. Okay, so also by chain rule, I have this expression for this j prime acting on delta g. So if I use this, then I have this identity. I put it in here. Okay, I have this identity, and u prime is the Gatto derivative of u. Okay, that appears in this chain rule here. Okay, and if I use this adjoint of j prime, I have this identity. Now everything is in terms of okay, you have delta g appearing in the inner products. So if I go back to the cos functional and compute these two gradients, gradient of u j hat with respect to u and gradient of j hat with respect to the control g, I will get explicit expression from the cos functional, that is integral of u minus ud squared and integral of g squared, right? Okay, I put it there, I get this simple expression for the gradient of j hat. I can pull this out now, right, because delta g is arbitrary. So I get the expression for the gradient of j hat. And to compute this adjoint, I have to solve adjoint equation of the Navier-Stokes equation, which is this. For the cos functional, I had this L2 norm of u minus ud squared, so that appears in the right hand side. And this is coupled to the state equation through this state u. U is the velocity in the Navier-Stokes equation. Okay, this is the adjoint pressure. See, the divergence condition similar to Navier-Stokes equation appears. And I had zero boundary condition for the velocity. So I have for the adjoint velocity also have zero boundary condition. Okay, so I can compute the gradient by solving the adjoint equation. Okay, so this quantity is my adjoint variable z. Okay, so that if I solve this, I get z. I put it in here, and at to alpha g, I get the gradient of the cos function. So let's look at the steepest descent method, which says given initial control, this is the initial guess for the control, you perform these steps in an iterative manner. Okay, in the first step, you solve the Navier-Stokes equation given the initial guess g0, get the velocity approximation, pressure, and then solve the adjoint equation I just showed you, get zk and qk. Okay. So you can do this separately. First solve the Navier-Stokes and then get uk, and you need that to solve adjoint equation. Solve the adjoint equation. Once you have zk, that is adjoint of the velocity, you can compute this gradient of the cos function. Okay, is equal to zk plus alpha times gk. Alpha is a parameter that appeared in the coarse functional penalizing parameter. And once you know this gradient of the coarse functional, you can compute the direction. You go in the negative of the gradient of the coarse functional direction. Okay, and with that you can update the control. Okay, tk is some step length that allows you to take small fractions. You don't want to take this thing too large, because if you go too large and may not converge. So there are methods, for example, Amijo's rule and all sort of method to compute this tk. I think Protas also mentioned this thing, how to do it. You just have to take this expression and put in here, and then you use simple algebra to compute that step length. Okay, so that method is the basic method available among the gradient-based methods, which is although simple and converges only linearly. So it's not so attractive. Convergence is slow, so it's not very efficient, but it can handle control constraints very nicely. If you have, say, a constraint on the control G, say it is bounded below by GA and bounded above by GB, then when you update this control, let me show you that. When you update this thing, just have to make a simple projection. Okay, so you have this thing and then you project it using this definition. Okay, this is a simple formula to make sure that your control always stays within this constraint. Okay. So as I said, these methods are very slow, but it can handle these control constraints very efficiently. Typically, they converge fast, and then towards when they approach the solution, it converges fairly slowly, because often the gradient becomes flat, so it doesn't improve the convergence as it approaches the optimal solution. Okay, so if you are not happy with this method, there are nonlinear conjugate gradient methods. They perform little better, but they are also considered linear type methods. On the other hand, there are Newton's method. These methods converge a lot faster. Ideally, they converge quadratically. And on the other hand, they require a lot more smoothness in general. Now, for example, you need to have second derivative information available so that you can use these methods. So let's look at this Newton's method. What it does is it computes the gradient of the coarse functional, set it to 0. That is basically necessary condition of optimality, and you apply Newton's method to this necessary condition of optimality. So think of this as you have seen Newton's method in other contexts, like solving nonlinear equations, right? So here also same story. You apply the Newton's method to this equation. Now this is gradient of j hat equals 0. That leads to this form for the Newton's method. So this the delta squared j hat represents the Hessian second derivative of coarse functional. That is equal to minus of the gradient, and you solve this thing and update the control. Okay. Once you have delta g, you add it to gk, that gives you a new control. Okay. The difficulty with this Newton's method is it requires computing this Hessian, which is often a large scale matrix in the discrete case. So inverting that can be computationally very costly. So you can instead use iterative methods for just for this step. This is just a linear algebra problem. Okay, here you have matrix and you are unknown. This is often known right hand side. Okay, so to solve this linear algebra problem, you can apply iterative methods like Krylov subspace method or conjugate gradient. If that is the choice, so you don't have to form the matrix. What you have to do is you have to compute this product or action of this Hessian on this delta G, the multiplication, and then these iterative methods compute the residuals. So matrix formation is not necessary. And I'm going to skip the detail of derivation of this whole thing, but this is the kind of steps you have to take if you want to use these iterative methods to efficiently compute the Hessian. So first you solve the Navier-Stokes equation for U and adjoint Navier-Stokes equation for Z, and solve the linearized Navier-Stokes equation for delta U and delta P through this equation, and then calculate delta R, that is given by this formula, okay, and then solve the adjoint Navier-Stokes equation for delta C and delta Q with the right hand side that is now this thing instead of U minus UD, okay. That will give us delta Z and delta Q, okay. Then return to this expression or you compute this action of Hessian on delta G through this formula, okay. So that is the Newton's method and implementation. There are quasi-Newton methods, just these are like Broyden methods available. Instead of computing exact Hessian, you can compute approximate Hessian. These typically store and accumulate the gradient information, and from iteration to iteration, they update this Hessian approximately. Due to the large scale problem with fluid flow control problems, these BFGS or Broyden type methods can be useful. And also with Newton's method, there is an issue of globalization. That is, this Newton's method do not converge with arbitrary initial guess. That is, well known in Newton's method for solving nonlinear equation, right? You had to start off close to the solution. So this method requires, Newton's method requires globalization. Simple way to do that is to perform a few steps of gradient iteration that I explained, for example, steepest descent, which is slow. You switch to Newton once you have sufficiently close solution, okay. That is a simple way to globalize it. Now, if you want to insist on using Newton's method, as I said, it requires more smoothness or regularity of the solution. And when there is a control constraint, computing the second derivative and all that thing can create problems. For example, the optimality condition with the control constraint becomes this inequality, okay. So you can convert this inequality into an equality like this if you introduce additional adjoint variables on this. So mu A and mu B are the adjoint variables associated with GA and GB, okay. And you also get this complementary conditions, okay, to deal with. The method, Newton's method, standard Newton's method won't work. You would have to use something like a interior point method or primal dual active set methods if you want Newton's type method for solving these constraint control problems. Now, how about point-wise state constraints with Newton's method? There are constraints, state constraints, point-wise state constraints on the state variable, say like this, U has to be between UA and UB. Then the solution has to be continuous in omega bar. So the Lagrange multipliers, mu A and mu B, associated with this point-wise state constraints measures, okay. So that create some problems because usually the adjoint equations are regular, and since the adjoints with there are measures that appears on the right hand side, the adjacency equation loses regularity. Okay. So with Newton's method, if you have state constraints, then you have to regularize the problem. One way to do that is to introduce some sort of mixed constraint. But this epsilon is a small parameter. You add this quantity to u. That makes the problem, see, you have mixed constraint, control and state constraints. Okay. Then you write down the joint equations, just like in other case. The optimality condition becomes like this, and you also have complementarity conditions. Okay, there is another popular regularization approach, that is Yoshida approach. That simply goes into the cos functional, and
you want? No, come on.
So this regularization simply modifies the cos functional by including this state constraint into the cos function. Okay, so that's the way it handles. Now let me talk about this intrusive methods or all advanced method. I'll talk about just one method that is quite popular. These methods treat the control and state variables as independent optimization variables coupled through the PDE constraint. Okay, PDE is kept explicitly as a site constraint. It also uses second derivative information, just like Newton's method, but here it treats control and state variables as independent variables. Okay, and it also linearizes, linearizes state equations during the iteration. And as the iteration converges, PDE constraint is satisfied through the convergence. And also the optimality and feasibility are approached simultaneously. An advantage here is the repeated evaluation of nonlinear equation is not necessary. The PDE doesn't have to be nonlinear. You can use a linearized version of the PDE. This method is equivalent to applying the Newton's method to the optimality system, which consists of state equation, adjoint equation, and the maximum principle. So if you apply Newton's method to this optimality system, that is equivalent to the method I'm talking about here. It goes by another name, that is sequential quadratic programming method. So suppose you have an optimal control problem where you minimize cos functional subject to the constraint C equals 0. Then you introduce a Lagrange multiplier. You multiply this thing and add it to the cos functional. That gives you a Lagrange. Okay, and this SQP method comes up with a quadratic approximation to the cos functional and replace the cos functional by the quadratic approximation. Think of this as some kind of tail expansion approximated to the second order, and then linearizes this constraint and uses that as a constraint for this quadratic programming problem. Okay, so here you have a quadratic cos. These UK and GK are all given state and control. So you are minimizing a quadratic cos subject to an approximate linear constraint. Okay, so given UK and GK, you solve this problem. Of course, this is a constraint minimization problem, so you apply optimization technique. Convert this into optimal system, solve the optimality system, update UK and GK, come back here and solve this problem again. Okay. So that's why I said you don't deal with nonlinear equation. You come up with a linear representation of the state equation. So for a given iteration, you solve this problem. Okay. All right. So the SQP method is equivalent, as I think I said this before, by applying Newton's method to the optimality system. And there are similarities between SQP and Newton's method for the reduced problem. Newton's method to the reduced problem is different from applying Newton's method to the optimality system. Okay? If you apply Newton's method to the optimality system, that gives you SQP. But there is Newton's method that you can apply to the reduced cost function if that is suitable, if you have a unique solution and so on, right? But there are similarities. For example, state and adjoint states are exactly solved when Newton's method is applied to the reduced problem, okay? Because that uses nonlinear state equation, whereas SQP, that uses linearized version of the state, and adjoint state is also linear, okay? And with unsteady Navier-Stokes equation, if you have this, if this is an issue, solving nonlinear problem at each step is an issue, you can use semi-implicit discretization scheme and so on, because since it's an iterative method, during the iteration you can use semi-implicit method, which may not be as good as fully implicit discretization schemes. It still gives you a decent solution. Okay, so with that, I'm going to move on to a computational problem. So in this part, I'm going to talk about optimal control problem for control of convection in binary mixtures. Okay. In binary mixtures, the flow is modeled by a Navier-Stokes type PDE. I will describe this thing next. Then present the weak formulation and formulate a boundary control problem and show you the penalized boundary control formulation. And talk about the first order necessary condition of optimality, maybe in detail, which I did not do in the yesterday, for example, and then show you some computational results. Okay. So here is a motivation for this control problem. Controlling convection in binary mixture has many applications, including convection in solar pond, because convection in solar pond leads to erosion of gradient zone.
What is the
Solar pond is just solar pond.
What solar pond? What is the application?
It's energy generation. Energy.
Solar panel.
Yeah. No.
So it's a water.
Water. Yeah.
But you absorb and convert
Solar,
the
yeah.
solar energy to something useful.
Some
Is that it?
energy. Yeah.
So what do? You get energy, extract energy.
Yeah.
Okay, we'll talk later.
Yeah.
Understand what you
In solidification of crystals, convection can be an issue because it leads to macro segregation, that is compositional variations. Convection can also affect the uniformity of the crystals that you form, and also the speed of growth rate. Convection leads to rollover instability. This is a phenomenon that happens in storage and transport of liquid nitrogen gas, and also fire phenomena with petroleum mixtures. So these are some of the applications where controlling convection in binary mixture is of interest, and these are modeled by a coupled Navier-Stokes equation where the coupling is through concentration field, where a two-way coupling, a concentration dependent density in the buoyancy form, a buoyancy term, and back coupling known as Sorey effect. This is also known as thermal diffusion. And here I'm going to employ approximation known as Bosnisk approximation. In Bosnisk approximation, temperature variation and concentration variations are assumed to be small, and therefore the density variation is small, except only in the buoyancy term. So in other places in the governing equations, you can assume the density variations are negligible, so basically constant. With that assumption, the double diffusive convection model takes the following form. You have a conservation of momentum. On the right hand side, I'm employing this Bosnisk approximation. So equation of state gives me density in terms of temperature and concentration S. Temperatures I'm using for theta. I'm assuming the density variations are small elsewhere. Therefore, this is a conservation of momentum. This is conservation of mass. This is conservation of energy. And theta is the temperature. U is velocity, P is pressure, and S is the concentration. This is conservation of specie. I have these fluxes here. These are generalized Fourier law, and also so flux is generalized Fourier flux and fixed flux. Okay, and we have expression for the fluxes, and the second terms in these two. Yeah.
What is the last word in the first line?
This thing?
Yeah.
Oh, species.
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 So what,
Oh, okay. Yes, there's an S.
what do you
Yeah.
mean by this?
Yeah, think of concentration. Okay, here.
So what is concept?
Concentration.
Momentum, mass, energy, but what is? How do you mean this?
So it could be some scalar.
Yeah, it's a scalar field. Yes. Yeah.
Stochastic scalar. So it
Yeah. Think of salt.
Ah, okay.
Think of salt in a fluid. Yeah.
So
Okay.
it could be just one equation or maybe 10 equations. depending
Yeah, it
on
could
the-
be. Yeah. Yeah. I'm just using one species.
In combustion, you have many components. All of them have one
Yeah. Okay. So these fluxes have this expression in the standard Fourier law and fixed law. You don't have these extra terms. These two terms. Okay. And here I'm including that because in chemical vapor deposition, for example, this some of these quantities are important. You cannot assume they are negligible. Usually we assume these are negligible quantities, especially the Sorey effect. That is this term, modeled by this term. That is important in chemical vapor deposition. Whereas this is known as Dufour effect. That is negligible in liquid mixtures. So let me ignore the Dufour effect, and then after some non-dimensionalization, I get this couple Navier-Stokes equation modeling double diffusive convection. Okay, here PR is a Prandtl number, and this is Grashov number. This NR is buoyancy ratio, and I is a unit vector. Okay. So the Sorey effect is modeled here by this Laplacian term. This is some coefficient, L is a Lewis number. Okay. So I'm going to assume, just for the analysis that I'm going to do probably for the next 15 minutes, the boundary condition for temperature and concentration are 0, and for the velocity, I'm assuming that is control everywhere on the boundary. Okay, and I have some initial condition for velocity and temperature and concentration. Okay, so I'm going to control convection, which this convection here is modeled by velocity. So if I have non-zero velocity, I have a container where fluid is active. It's a closed container. I will when I do the computation, I will show you the exact configuration. So I want to drive the velocity to 0 by applying control on the bound.
Read the last equation for S, because the green things we can't see.
Oh, this thing?
Yeah,
is alpha star of LE. There, huh?
So just the green thing.
Oh, okay. Alpha star over LE delta theta. Theta is the temperature. Okay. So it couples this. It gives you a back coupling to the well, various other equations to this and okay, other equation. Okay. So this is an interesting problem. So I will put this problem in the weak formulation that I discussed yesterday, okay, and talk about few of the things that I did not cover okay, yesterday. Okay, so the weak form for this thing, this model is the following. Given G and initial condition for velocity, temperature and concentration, and the right hand side, this right hand side appears here. Okay, I assume this is L2 its inverse. So we want to find a solution U theta S in this solution space. I will describe that later. Satisfying this weak form of the double diffusive model, which is a coupled Navier-Stokes equation. Okay, and this hold for all V P psi in this V times H10 square. Okay. These are some of the function spaces I used. This W is W1 times W2 and W1 is this space. I wrote down this yesterday too with the norm defined like this. And W2 is similarly defined. Okay, L2H10, so that time derivative of phi in L2H inverse with this norm. Okay. And for the analysis, I will assume omega is bounded set in R2 with Lifschitz boundary. And I define this space W1 sub gamma to be the trace of functions in this W1 on the boundary, the space-time boundary with this norm. Okay? Okay. So, this is the Well-Posner's theorem or lemma, which is a counterpart of what I wrote down yesterday and day before yesterday. It simply says there exists a unique solution U theta S. P is not unique, by the way. It's a typo. In this space, satisfying these a priori estimates. Okay. Okay. Now, here's the coarse functional that I will use in the computation. My goal is to stabilize the no motion state. Okay, so let me give you some detail here. So I'm going to look at in the computation. I'm going to look at problem that I want to stabilize an unstable state. So I will look at a simple rectangular geometry. Okay, where I apply temperature on the left, temperature boundary condition, and concentration equal 1. On the right side, temperature is 0, concentration is 0, and on the top and bottom boundaries apply insulation boundary condition. D theta dn equal 0 and ds dn equal 0. Okay. And for this boundary condition, there exists a steady state that is that involves zero velocity and non-zero temperature and concentration. Okay, so that is a no motion state. And what happens for a large Grashov number that appears in this, I can show it here too. Yeah. This is the Grashov number. Prandtl number is typically fixed for a given fluid and usually small in the order of 1. This can be large. Okay. For small Grashov number, you have a no motion state, that is velocity is 0, fluid is at rest, and you have temperature gradients. Yes, the boundary on left boundary we have temperature equal 1, on the right is 0. So you have a simple solution like this. U equals 0, theta equals 1 minus x, s equals 1 minus x. If you further assume the nr that appears on the right hand side of the momentum equation is equal to minus 1. You can easily check. If you substitute this solution into this, if you set u equals 0 everywhere, okay, you can easily verify that solution satisfies the Navier-Stokes equation and the concentration and heat equation. But when the Grashov number is large, that steady state loses stability, and you get a non-zero solution. Okay, that is what I call convection generation. So by applying control, I want to stabilize that that state. I want to bring that non-zero velocity down to 0. Okay, so that is the control problem. So I introduced this cost function, the best cost function to minimize the deviation between u and 0. Okay, and ideally you want to do it in L1 norm, for example, right? But that is not differentiable and so on. It's difficult to work with. So I'm minimizing this L2 norm of u. Okay, and what is this term doing here? I'm introducing this just for the sake of theoretical analysis. Okay, that gives me a lot more smoother functional to work with. If you have listened to my theoretical analysis talk yesterday, I was using a lot more. I didn't use the L2 norm. I used some kind of weighted H1 norm, right? So so this term is there just to get the theory going. Okay. If I don't put this, I won't be able to do the theoretical work. Okay, for computational work, I don't really need this. So what do I do is, I take this delta sufficiently small. Okay, so let 10 to the minus 4 or something. Okay, so it is not really there, and that helps to get my goal achieved. Okay, so this is the cost of the control. Okay, okay. So this is the cost functional I will use in the computation. And also in the theory, I can make it a bit more general, like vorticity or this, or in general theta satisfying these two conditions. Okay, so this is something I presented in the yesterday's class. So let me define a penalized boundary control problem. You have seen the weak formulation. So the penalized boundary control problem is to find, for each epsilon, find a control G epsilon such that the cost functional is minimized subject to the penalized Navier-Stokes equation. Okay, my admissible control set is this. Okay, so today's talk I'm going to talk about the adjoint equation derivation. Okay, so I will start with first order necessary condition of optimality. And then use that to derive the adjoint equation. So first thing you have to do is to verify this state to control map is differentiable. Okay, so this lemma says this map, control to state map, has a Gateau derivative d of ug in every direction h in that miscible set. Okay. Moreover, this derivatives u prime theta prime s prime is a weak solution of the what we call the sensitivity equation. Okay. Basically, derivative, Gateau derivative state equation. Okay, with respect to the control. Okay, so I'm going to assume this can be verified by simply taking Gateau derivative of the state equation. Okay, so if u prime satisfies this, then the state variables are Gateau differential. Okay, that's what the theorem says. Now, let's look at the proof briefly. I won't go through the details. Let's assume UG, theta G and SG, and this is the perturbation. These are U, theta, S here, solutions for the control G plus lambda H. Okay. So let's say these two are solutions of the Navier-Stokes equation with different control inputs, G and G plus lambda H. Then I want to show the Gateau differentiability of this, right? That is equivalent to proving this. Okay, 1 over lambda times, this is basically a definition of Gateau differentiability of this with respect to G. Okay, so as lambda goes to 0, I want to show this goes to 0 with respect to the norm. Okay, okay. So to prove this thing, I'm going to go in 2 steps. I want to first get some estimates on the difference between these two. Okay, so I introduce auxiliary variable u tilde theta tilde s tilde be the difference between these two. That is nothing but this. I'm going to get some estimate. In fact, I want to prove in this norm, the norm of this thing is ordered lambda. Okay, lambda is this this parameter. Okay, okay. So to prove that, what you do is you use the fact that this u tilde theta tilde s tilde satisfies this system. I simply subtracted those two Navier-Stokes equations. Okay, I get this equations for this u tilde theta tilde s tilde, and then I estimate this using energy arguments. Okay, you get this differential inequality. Okay, h is the direction. Okay, and then applying Grunwald arguments, you can show what you wanted to show. That is this norm of this thing is order lambda. Okay, and you can show you can show these quantities finite using this Gladio-Rumberg inequality and so on. Okay. So now let's prove what we want to prove. That is showing this this quantity in this norm is order lambda to some non-positive power. Okay. So again, I'm going to use the fact that I can subtract appropriate equations for the terms appearing in. Let me see. Yeah, for this one, I have an equation. This is a sensitivity equation. Okay, for u tilde, I wrote down an equation, so I subtract those two, and then again, estimate the terms using energy arguments and Grunwald inequality, and I can get this thing. This is what you get when you apply energy arguments. Okay. And then since this norm is order lambda to the power 3.5, you can take the limit as lambda goes to 0, and this thing is the whole thing here. Okay, so we get Gateau differentiability. Okay, now let's turn to maximum principle. So what I proved is just a Gateau differentiability of the state variable with respect to the control. Now let's look at the control maximum principle. That says if you have an optimal solution, then you have a necessary condition of optimality, or this this is true if you have optimal, so if the U epsilon G epsilon is optimal, then you have this identity. Okay. Then this identity says in every direction the derivative, Gateau derivative of J must be 0 for all directions H. Okay. So that is the maximum principle. And from this you can come up with the explicit expression given the using the cos functional. So you can easily convert this maximum principle to this identity. Okay. Now this thing U prime is the sensitivity or the Gateau derivative. Okay. And Gateau derivative is not convenient to work with in computations. So because you have to take for all G and satisfy this condition. On the other hand, if you use adjoint, then you can just work with one adjoint equation and get the gradient. Okay. So let me talk about the theorem that allows us to connect this maximum principle to adjoint equation. That says if U epsilon, theta epsilon, S epsilon, D epsilon be an optimal solution to the control problem, then this identity holds. So the maximum principle becomes this. Okay. And here this U, I'm using a very fancy notation here. This quantity is the adjoint velocity. Okay. And that satisfies this adjoint equation. Okay. And the adjoint equation is as a negative sign here. So it's a kind of backward parabolic problem with the final condition. Okay. So let's look at a proof of this thing. Suppose this U epsilon, theta epsilon, S epsilon, G epsilon be the optimal solution to the control problem. Then I can take the optimality condition. I'm going to perform integration by parts. So this is a pretty straightforward calculation. Okay. So I take this maximum principle. Okay. And I'm going to perform integration by parts. Okay. So if I use the sensitivity equation, okay, I'm going to start with the momentum equation. Okay. And that gives me, let me go back to the, yeah. So I'm going to take this thing, this equation, and use this term. Okay, this one doesn't have adjoint, it has this Gateau derivative. For that we have another equation. Let me see. Okay, that is this. Okay, so I'm going to use this one and this equation to simplify this term. Okay, so that is done through integration by parts. Okay. Okay. So if I take this thing and then if you use the sensitivity equation for the energy equation, you can rewrite this term in this way. This is a sensitivity equation for the temperature equation. Okay. So you take this term and use the fact that it satisfies this, plug it in here. Okay. Similarly, you can take the concentration equation, sensitivity equation for the concentration equation, and come up with the expression for this. Okay. And then you substitute these two in here, and then perform integration by parts. Okay. So this identity helps us simplifying that further. Okay. Why these are 0? Because if you look at this thing, this adjoint variable, and that satisfies final condition. This is 0 when t is capital T. This T prime is sensitivity, that I differentiate the that I obtain by differentiating steady equation. So that satisfies initial condition, which is 0 because you are differentiating, right? So this thing is 0. Similarly, you can show this is 0. Okay. So these things we use in further simplifying. Okay. So I performed integration by parts on those terms and moved the derivative on the adjoint. Okay. Similarly, you perform integration by parts on the adjoint equations. Okay. May not make much sense at this point. So finally, you arrive at this formula. Okay. Now integrating by parts on the time derivative term, that is here with respect to time. Okay, I have integral, so I can perform integration by parts, move this derivative onto that. Okay, that allows us to use the sensitivity equation to remove some of the terms here. Okay, and finally you arrive at this maximum principle. Okay, in terms of the adjoint. Okay, so that basically proves the theorem. Okay, so let me now move on to the computational part. So this is the problem I was talking about on the blackboard. I have a configuration here, a closed domain. On the sides I apply temperature gradient and concentration gradient. On the top and bottom wall, it is insulated. Okay, so you apply those boundary conditions applied there, and this is the momentum equation I had with nr equals -1. Then see you have this minus sign. Now you can easily verify this when you set u equals 0 and theta equals 1 minus x and s equals 1 minus x. X is the spatial variable. It satisfies this equation. So in other words, this is exact solution to this. Also, it's steady state. It's a 0 solution, and I want to preserve this for all, ideally for all Grashof number, at least for beyond the critical Grashof number. Okay, so basically, this problem is about stabilizing an unstable state. Okay, if you simulate this problem without control, you will see as you increase the Grashof number, this no motion state will lose stability. You will see non-zero velocity appearing, that is in the form of convection, convective circulations. And if you increase the Grashof number further, you get more bifurcation. So this single circulation becomes a multi-circular solutions and so on. So the goal of the control is to suppress this convection. Okay, I'm going to apply control on the top and bottom boundary. So to begin with, let's suppose we have control on the bottom boundary in the form of boundary wall movement. Okay, I'm moving the boundary wall in the entire boundary. Okay, that is the control action, and my goal is to suppress the convective motion inside the cavity. Okay, on the sides, on the left side and right side, I apply fixed boundary condition as I prescribed there. Okay, and I'm taking a Grashof number that is above this critical Reynolds number, Grashof number for which you have convective motion. Okay, and Prandtl number is taken to be 1 and the Lewis number is taken to be 2. Okay, and here is the computational result. First one illustrates the convergence of the penalty parameter epsilon. This is something I use to penalize the boundary control, and what you see here on the left is velocity against time measured at a point, spatial location near the right corner, x equal 3/4, y equal 3/4. So I'm just measuring the velocity, only u component, okay, at a fixed point and over a time interval. So This shows as epsilon is decreased, you have convergence. Okay, here some of the figures are indistinguishable because the solution has converged. Okay, on the right you see control again for different epsilon values. Okay, again you see as epsilon is reduced and goes to 0, the control curves converges. Okay, become indistinguishable for these two epsilon parameters. Okay, now this one shows the optimal placement of control action. Okay, I chose full bottom control, that is you move the entire bottom wall or entire top wall, or you could move, as I pointed out here, you could apply control on a portion of the boundary, the middle part or on the left part or the right part, or you can apply control for the entire boundary. This result illustrates the effectiveness of control depending on where you place the actuation. Okay, and of course the full bottom control, if you move the entire bottom or apply control in the entire bottom wall, that produces better result. This is again just a velocity u. Okay. Okay, and the right bottom performs poorly. Okay, that is basically v velocity. Okay. Okay, well, this compares. I think that the control at the middle of the wall. The bottom curve shows the control that you want to when you apply the control at the top wall. That corresponds to control the bottom wall. Okay. This one, okay. Here I studied the effectiveness of various cost functionals. See, the cost functional I used is minimizing the velocity in L2 norm. All right. And if your goal is to drive the velocity, non-zero velocity to 0, or to this state, this is your desired state, then there are other possibilities. For example, you can use tracking of temperature, for example. Right? You can use T or theta minus theta d, or theta minus that, this, let's call this theta d. Okay. So you can use theta minus theta d and minimize it in some norm. I'm using L2 norm here. Okay. All right. This is also a possible cost functional to achieve your objective. Yeah, because this is your desired temperature. Although you want no motion state, if you drive the temperature to this, you can hope to get 0 velocity. Right. The other possibility is to look at tracking of temperature. Okay. So why didn't I look at these these cost functions so far when I was talking about all this theory, well, I cannot prove theorems with this cost function. Okay, even with this, that's why I added a delta times gradient of u term in there. Okay, so computationally you can implement it. It works. So that is the point of this computational study. We were able to show there are other cost functions that you could use computationally, although we could not prove it. This will work. All these convergence theorems. This J stab, this simply corresponds to that cost functional, you see. Okay, the minimizing simply L2 norm of u. Okay, this T track correspond to tracking the temperature. Okay, and this one tracks both temperature and concentration. Okay, the vorticity corresponds to minimizing L2 norm of curl squat. And this JS track corresponds to tracking the concentration just like that. Okay, and among all these, okay, this one corresponds to velocity for no control. So this uncontrolled u at a point at the same point, x equal 3/4, y equal 3/4. This is uncontrolled velocity, and these are controlled. This corresponds to these are controlled ones. Okay, and on the right, so you see the controls corresponding to these different j's. Okay. This is basically the results that shows how the weight parameters. I forgot to write down the weights. In front of this term, we typically put gamma over 2 and here delta over 2, right? Some weights, and we play with this weight and make sure your objective is achieved with minimum control. Okay, in other words, you don't want to spend too much control, right? At the same time, you want a bounded control. So this shows the effectiveness of those parameters, various values. Okay, all right. So this is the velocity profile, so velocity plots. This is uncontrolled velocity field with no controls. This is with control on the bottom part, bottom wall. So it's basically moving the bottom wall. We were able to bring the velocity to 0. So if you can see, although it has the colors, you look at the values, shows it's all 0, near 0. Okay, so the control action indeed brings this non-zero velocity to 0 velocity. Okay, and these are uncontrolled temperature concentration, and this is controlled concentration. Okay, contours. Okay, this is uncontrolled temperature here on the left, and that is controlled temperature. Okay, I think with that I will stop. Okay, thank you.
You can compute the control in real time. That's what it is basically, right?
Yeah, but I didn't use any real-time methods. This is using the Newton's method.
Yeah. So this is steady solution.
Huh? No, it's time-dependent solution.
So yeah. So time dependent solution, so you're computing the control as it evolves, right?
Yeah. I solved Newton. I used Newton's method. Okay. Solved the joint equation.
Yeah. So intuitively, let's say you're applying the control. So as you're trying to update the control. In the meantime, the flow evolves. Right? So so Newton method has to converge before the next time test step, because there is a. How do you real time implement this? That's my question.
No, I didn't. I mean, you cannot implement this in real time.
Why?
Because the method I used is not suitable. You don't get the real time answer.
But you look at, you know the optimal control in time.
You mean in advance?
No, as it evolves. Yeah, so that's probably the point you have to clarify. So you find the control function, but you sort of so then that.
Yeah, you solve the Navier-Stokes forward in time.
Yeah, and then
and then you solve
a
a joint equation backward in time, the entire time interval, update the control. It's an iterative process, right? It's a nonlinear control.
Then, so in order to implement, you probably have to run this, get the optimal control.
Yeah, you have to store the state equation solution. Yeah, you have to solve it at each time step, or you have typically store it in post grid, time
You
grid.
have to maybe store the optimal control somewhere and then you apply.
Yeah. Right. You have to store the adjoint also.
Yeah.
Typically store it on a post grid and then interpolate if necessary. And typically you have to do that, otherwise it is storage demanding.
Question.
When you spoke about the steady state problem, when you assume that G is small or nu very
Yeah, that is just theoretical.
is it possible to do it alternatively in the way that you expand your solution as a power series respect to G and just compute that finite number in the element of the power series? How would that's
power series, you expand what in power series?
No, I think what he's asking is expand the steady solution in terms of the parameter, right?
That parameter is G.
Yeah, yes, something like that's been done by Herb Keller. Herb Keller and also then Maidili Ramasamy when she was a postdoc, actually following the bifurcation. Something like that, right?
No. What I'm saying is that in the region when you have unique solution, you have power series expansion. And so I wonder whether this would make any sense numerically or not.
Whether you can go into the multiple solutions between
You can't go. Just block it.
Yeah, because the bifurcation point is not allowed.
That's all. Thank you.